All right, let's talk about something that's poised to completely change how we think about, well, building things. This isn't about some fancy new metal or a new kind of plastic. No, this is a revolution based on something way more fundamental, building materials whose amazing abilities come from their shape.
So, to get started, we need to talk about a problem that engineers have been wrestling with forever, and that is the vibration problem.
I mean, really think about that for a second. What if a skyscraper could stand perfectly still in an earthquake, or the camera in a rocket could get a perfectly clear shot during a launch? This isn't just about comfort. It's one of the biggest and most persistent challenges in all of engineering.
Because the thing is, these unwanted shakes and vibrations, they are literally everywhere. On a huge scale, they can weaken and even destroy a bridge. Inside a jet, engine vibrations create constant stress and wear on every single part. And on the tiny scale, it's what makes your phone's camera blurry or completely ruins a delicate experiment in a lab. We pour so much time, money, and energy into just trying to manage them.
But what if you could just make them disappear? Well, that's where this totally radical new solution comes into play. It's a huge breakthrough coming from a team-up between the University of Michigan and the Air Force Research Laboratory.
You heard that right. They have 3D printed an object that can just passively stop vibrations, dead in their tracks. There are no moving parts, no electronics, no power source. The object itself just does it.
And here it is. It's called a Kagome tube. The name actually comes from an old Japanese basket weaving style, and you can kind of see why. It looks like a chain link fence that's been rolled into a tube, and that incredibly complex geometry is its superpower. When a vibration tries to go through it, the structure's design basically traps that energy and cancels it out. It's almost like magic.
And this brings us to the absolute core idea of this whole explainer. The secret here isn't what the material is made of. It's not about the chemistry. It's about the geometry. It's all in the shape.
This quote from Professor Xiaoming Mao just nails it. Think about it. For all of human history, if we wanted to make something better, stronger, or lighter, we changed its ingredients. The Bronze Age, the Iron Age, it was all about chemistry. This is a completely different way of thinking. So this Kagome tube is part of a wild new class of things called mechanical metamaterials. And here's the crucial part. You could make this out of plastic or aluminum or some advanced composite. The base material itself doesn't really matter. The structure is what gives it its power.
This chart just lays it out perfectly. On the left, you've got how we've always done things. You want stronger steel? You change the chemistry, add more carbon. Simple. On the right, you've got metamaterials. You want a new property? You redesign the shape, the internal architecture. It's kind of like the difference between baking a better cake by changing the ingredients versus building a better cake stand out of Legos.
Now, as revolutionary as this all sounds, it turns out we're a little late to the party. Nature figured this out a long, long time ago.
I mean, just look at these examples. Our bones aren't solid rods. They're this complex, spongy lattice that gives them incredible strength without being super heavy. A honeycomb gets all its amazing rigidity from that perfect hexagonal pattern. You could say nature is the original metamaterial designer, achieving incredible performance by just engineering shape out of the simplest materials.
So how did we get from marveling at a beehive to actually 3D printing these advanced structures? Well, a breakthrough like this doesn't just appear out of nowhere. It's built on over a century of scientific progress. The breadcrumbs actually start way back in the 1800s with James Clerk Maxwell. Yep, the same guy from your physics textbook who worked out the basic design rules for stable structures. Flash forward 100 years or so, and mathematicians developed this whole field called topology. And then, just a few years ago, some brilliant researchers realized they could connect Maxwell's old ideas with this new math. That was the key. That unlocked the theory, which led us straight to today, where they can actually build the thing. And I just love this quote from James McInerney at the Air Force Research Lab. You can just feel the excitement, right? It's one thing to have a theory or a cool computer simulation, but it's something else entirely to finally hold the object in your hand and realize, wow, it actually works. Okay, so the theory is proven. The object is real. The question now is, what's next? Where do we go from here? What does this mean for the future of everything? Well, the researchers are pretty convinced that we are at a genuine turning point. The ability to manufacture materials from the ground up with this kind of geometric precision, it just opens up a whole new design landscape. We're not just making better versions of old materials anymore, we're creating entirely new classes of materials from scratch.
Of course, it's not quite that simple. As with any game-changing technology, there's a big hurdle they have to clear before you start seeing these things in your car or your washing machine. And here it is, the core trade-off. As of right now, the geometric patterns that are fantastic at stopping vibrations are also not so great at supporting a lot of weight. So you can have one or you can have the other. But getting both at the same time, that's the next big engineering puzzle to solve.
So the to-do list for scientists is pretty clear. Number 1, figure out how to balance that trade-off. But just as important is number 2. They have to invent whole new ways to even test these materials. I mean, when you create something with properties we've never seen before, all the old instruction manuals go out the window. You have to write a new one from scratch.
And that leaves us with this really fascinating final thought. For all of human history, we have built things based on the chemistry of the stuff we used. Now, we are learning to build with geometry itself. The question isn't just about stopping vibrations anymore. The question is, what other seemingly impossible properties can we design into existence, one shape at a time? What will we design next?